there are three types of friction. One is the linear friction known as viscous friction. It gives the friction torque is equal to Bm into theta m dot. That is, friction torque is proportional to the velocity. This is a linear part of that, also known as viscous damping friction. And next one is Coulomb friction, which is given by some Tc into signum function of theta m dot. And this is applicable only when the system is really moving, the shaft is rotating. That is when the magnitude of theta m dot is greater than 0. And the third type of friction is acting while the motor is at stationary condition, then when theta m dot is equal to 0. And its value is called static friction or stiction, which is equal to minimum of Ts and magnitude of Tm multiplied by signum function of Tm. I will explain this. Say if you are, for example, pulling your table, which is on the friction floor having friction, you are pulling the table. Before starting, whatever the force you have to apply is called, it is whatever force you apply, the pulling force on the table, that is counterbalanced by the stiction or static friction. And as you increase your pulling force, the friction also increases. If you are not pulling, there is no friction force. And this process will continue until your pulling force exceeds the upper limit of the static. That is called Ts. Upper limit of static friction is denoted by Ts. And the actual static friction force will be minimum of Ts and your applied force. If your applied force is 0, there is no friction force. And the sign of this friction force will be here sign of Tm, because it is we are putting this friction force as friction force itself in the opposite direction, because this is categorized as a load force. That is why the load force should be equal and opposite of the applied force. Already this is defined in the opposite direction. That is why we are giving the sign of Tm is given. If we are giving a positive Tm motor torque, then the load also will have a positive reaction force given by this. And this is applicable only for theta m dot is equal to 0. That is, the stiction is represented by this line plus Ts to minus Ts, but it can stay anywhere on this line. It can be anywhere on this line. You cannot, the actual value depends on what torque you are applying. If you apply a torque which is less than this plus Ts or minus Ts, the stiction will be equal to the applied torque, but the opposite direction. But if it exceeds, it will start moving. And the moment it starts moving, the friction force will be taken care by the Coulomb friction law. That is Tc into signum function of theta m dot. And this also, as I told, it is now I talked about a lot of logic. It is not that easy to simply simulate it. We will take it as a separate example in our lab. But for time being, we use only these two friction motor. These already we have taken care in the motor equivalent dynamics, BM value, BL, etc. we have taken. And now we will take this also. There is a simple signum function, friction alone we will take. And the static friction, model we will take subsequently. Okay. Thus, I will, this nonlinear portion is finished. Now we'll go to another important portion called frequency response of nonlinear dynamical system. In the linear dynamics, you have started with that only. By this time, you have covered Bode plot, Nyquist plot, or at least Bode plot, I hope. Am I
No,
right?
sir. No, sir, we haven't started
No,
yet.
sir.
So where are you now?
So we are going to start Fourier.
Fourier or Laplace transform.
Sir, you're talking in signals and systems, right?
How much you have covered? Signals?
Yes, sir, we have to start Fourier. We have done Laplace in previous semester.
Okay, Laplace you are done. Okay, that itself is frequency response only. Only difference between Laplace and the so-called sinusoidal frequency response is, that is what I am going to show now. There is a next portion. I will explain that. There is a frequency response of linear dynamical system is independent of input command amplitude. You have seen the step response at least of linear system, right?
Yes, sir.
In step response, if you now already you have familiar with the Simulink, if you give a step command of say 1 volt, then 2 volt, 3 volt, in all the cases, if you don't use the nonlinear blocks, the rise time will be same irrespective of the amplitude. For 10% command amplitude or 20% command amplitude or 100% command, everywhere rise time will be same. That is a property of linear dynamical system. That is a performance parameters will not be affected by the amplitude of the signal. Similarly, if you take the bandwidth, it will be, if you give 1 volt sinusoidal command or 2 volt command to find out the bandwidth will remain same only. That is called the linear system response. Or in another way, if you plot the step response for this for 1 volt, this for 2 volt, suppose this is the step response for 1 volt command. Then the step response for 2 volt command will be like this. Both will have the same peak time. Both will have the same rise time, the 10% to 90%. Both will have the same settling time. So the performance will not be affected by changing the level of the command amplitude. That's what I'm telling. That's a property of linear dynamical system. Similarly, if you take the frequency response, there is something called bandwidth. It will come like this same characteristics you will get for 1 volt command sinusoidal signal, or if you take 2 volt command sinusoidal signal, or 5 volt command sinusoidal signal. You take the input output property and take the bandwidth. The ratio of output amplitude to input amplitude, that will remain same if the system is a linear dynamical system. But if you introduce nonlinearity, this frequency response will become different. If you increase the amplitude, frequency response, the bandwidth will come down. Similarly here, if you increase the amplitude, suppose this is the step response of 10% or 1 volt, then if you give 2 volt command, the step response will be something like this, which will take more time to reach its full value compared to the previous one. This effect of nonlinearity. So this is what now we for step response point of view, you have separate session for finding the rise time for different command amplitudes. Similarly, we'll consider how we can find out the frequency response for different command amplitude. The frequency response of nonlinear system is a function of input command amplitude. In transfer function, you have taken the Laplace transform of impulse response. So Laplace transform of impulse response is nothing but Laplace transform of unit impulse response is the transfer function, and you also call it as the Laplace transform of output by Laplace transform of input. For any command, it need not be impulse and all. If you give any RS command, you are getting YS by RS is equal to transfer function GS. What does it mean is, if you double RT to get twice RS, then YT also will get double, because it will follow the superposition theorem and the ratio will still remain same. So transfer function is invariant. It is irrespective of the command amplitude. But that will not be the case for nonlinear system. Now, and hence we cannot use the Laplace transform concept to derive the frequency response of nonlinear system. We have to go for numerical approach. So this is evaluated. How we will do that? We will evaluate this by taking the amplitude of fundamental harmonic of the system output to the input sinusoidal command. So we are going for the equivalent definition of frequency response. So what is the frequency response? We are comparing the output with respect to input for a specific frequency. For a specific sinusoidal command means it is having a specific frequency. But for nonlinear system, if you give a sin omega t as command, the output will contain not only sin omega t, of course cos omega t will be there, that is not a problem. It will contain sin 2 omega t, sin 3 omega t, etc., etc. Similarly, cos 2 omega t, cos 3 omega t, like that. That is, the output will contain harmonics of the input. So there is a need to redefine the frequency response when we come across with a nonlinear system. Simplest direct extension of the normal frequency response concept is, you take only the fundamental harmonic of the output and compare with the input. Take the amplitude ratio of the fundamental harmonic. That's what I have written here. How we can take the frequency response is taking the ratio of the amplitude of the fundamental harmonic of the system output to the input sinusoidal command amplitude, and also the phase lag of the fundamental harmonic of system output with respect to input sinusoidal command. So a MATLAB program is developed, and Mr. Abhilash will give you the MATLAB program, how to compare that. Now I am only discussing the theory behind it. The MATLAB program has two parts. One part is it will generate a sinusoidal sweep command of the specified amplitude and frequency range. And the second part is to extract the fundamental harmonic amplitude ratio and phase lag. For example, first we will fix the amplitude as a 5% of the maximum deflection. Suppose the rocket engine, we deflect plus or minus 5 degrees. Initially, we take only deflection, maximum deflections plus or minus 0.5 degree, and vary the frequency from very low frequency up to highest frequency of interest. So we generate a sinusoidal sweep command. Sweep in the sense that it will not be a single frequency. Initially there will be some comment, then we'll change the frequency, we'll go to high frequency, because it's difficult to draw here. Then we'll further high frequency. So we'll sweep through multiple frequencies. Initially 3-4 cycles of low frequency, then you double the frequency, another 5-6 cycles, again triple the frequency, like that it goes. That you will study in your lab session. Now I am going to teach you how you will extract the frequency response if you do such an experiment out of that. First, since you told that you are not studied the concept of sinusoidal response based on Laplace transform, I am going to explain it. It is called steady state sinusoidal response from G of j omega. Steady state sinusoidal response. I assume that you know what is meant by GS, Laplace transform, the transfer function, okay? And you have studied the stable system, that is if all the poles of the transfer function are in the left half of S plane, the system is said to be stable. That is the moment you give a unit impulse command, its response, what will happen? G2, this is suppose unit impulse command you have studied, del T.
Yes.
Okay. When you give del T, the response is known as GT. Response of that system is represented GT. And if all the poles of GS are in the left half of S plane, if you give a del T command at 0, the response, initially there will be some transients will be there. Finally, this transient will settle down towards 0, so that limit of GT as t tends to infinity will be 0. That you have studied, I hope. This one, the statement I heard. Since the system is assumed to be stable, GT tends to 0 as t tends to infinity. That is the definition of stable system. Okay. If you perturb the system from its equilibrium point, it will come back to its equilibrium point as t tends to infinity. That's all. Now consider LTI stable system with unit impulse response GT, with GS is the Laplace transform GT. And if you give a sinusoidal command, say A sin omega t for t greater than or equal to 0, and ut equals 0 for t less than 0. This is the common definition of any physical system, because we assume that we start our experiment at time t equals 0, and before that time the input was 0, and the output yt is obtained by gt convolution ut, where convolution is given by 0 to t g tau ut minus tau d tau. We are not using the other convolution, that is minus infinity to plus infinity is not applicable here because of this ut that is 0 for t less than 0. So if you use the other, what will happen is, this is a causal system also, ut minus tau for the argument when it is negative is 0. That's why we are not extending the limit of tau to, if you use a tau which is greater than t, then the here the domain that will go to negative, where ut is equal to 0. So there is no point of doing that. Okay. And we are starting with the time from t equals 0 only. So this only is important. Thus yt is equal to integral 0 to t g tau a sin omega t minus tau. I am substituting for ut. Ut is equal to a sin omega t. So ut minus tau is nothing but a sin omega t minus tau, which can be represented in a more analytically tractable form using the exponential notation. You know that e raised to j omega t minus tau is equal to cos omega t minus tau plus j sin omega t minus tau. So if you take the imaginary part of e raised to j omega t minus tau, that is nothing but sin omega t minus tau. That only I have written. The sin omega t minus tau is represented by the imaginary part of e raised to j omega t minus 2. All other things are real, g2 is real, a is real. So that can be, g2 can be taken inside, and I can take imaginary as a common, because real into imaginary is always imaginary. It will not affect this imaginary operation. Okay. Now, the independent variable of integration is tau. So whatever t is independent of tau, and hence that e raised j omega t can be taken outside, and this equivalently represented like that. Here we are going to give the new substitution. Since the system is assumed to be stable, gt tends to 0 as t tends to infinity. That is, if you give a sinusoidal command, what will happen is, let us define a time called steady state time TSS, such that integral 0 to TSS g tau e raised to minus j omega tau d tau, it is much greater than TSS to infinity g tau e raised to minus j omega tau d tau. Why? You know that gt is nothing but the unit impulse response of the system, and the unit impulse response dies out as t tends to infinity, and e raised to j omega t, its magnitude is always 1 only. So 1 multiplied by g tau, g tau is a asymptotically diminishing term. So definitely there will be a time TSS such that beyond the time, the integrated value is almost insignificant compared to the integral up to the time t. There is no problem to assume this. If you say that it is not significant, it is significant, then we will go to another time. So as you increase the value of time, definitely because of the monotonic decrease of the amplitude of g tau, always you can find out a time. And that time I call as TSS. Also, what I mean is TSS means steady state. SS corresponds to steady state. All the transients settles by the time. That's the meaning. Thus, we identify a time called steady state time. It is defined in such a way that all the transients excited by a unit impulse command settles down. You fix the time. So if you fix such a time, and then the benefit is like this, you can say that integral 0 to TSS g tau e raised to minus j omega tau dou tau is almost equal to integral 0 to infinity g tau e raised to minus j omega tau d tau. All right, because the error part is insignificant. But there is a definition, you know, that integral 0 to infinity g tau e raised to minus j omega tau d tau is called gj of j omega. It is directly coming from the Laplace transform definition. Only thing, e raised to minus st is replaced by s is replaced by j omega. Now, e raised to minus st, that s is replaced j omega means gs can be replaced by g of j omega. Agreed? Okay.
Yes, sir.
Yes, sir.
Now, for t greater than TSS, we can approximate yt as. Now you assume that t is something which is greater than TSS. Yt is equal to a imaginary e raised to j omega t g of j omega. From where we are getting already unapproximated formula is there. This is the correct formula, yt. But if t is greater than TSS, we have a special value for this. This is nothing but g of j omega, g of j. So that I am substituting g of j omega. So a imaginary e raised j omega t to g of j omega. That's what I read. A imaginary e of j omega, g of j. Now g of j omega is a complex number. It is having a magnitude part as well as a phase part. That is represented by m omega into e raised to minus j theta omega, where m omega is the magnitude of g j omega and theta omega is the negative of the argument of g j omega. This I define by negative. I will show why. There is no mathematical problem. Because of this, I am giving minus. So this minus and this minus will cancel. Effectively, it will give a better physical meaning for theta omega.
Sir, can I ask something here?
Yeah, please.
Sir, shouldn't it be t less than TSS? Because we defined y of t from 0 to t, right? The integral. So shouldn't it be t less than TSS?
No. Say, what we are considering is, if t is greater than TSS, here, this particular integral is only up to t. Now I am adding some extra offset TSS to infinity. And this extra offset should be insignificant. If t is less than TSS, this extra offset is significant. Okay. So if in a physical point of view, you are considering a time when all the transients are died out. We have reached a steady state. Under steady state only, this equation is applicable. That is what I mean. Under steady state condition, once you ensure that all the transients have settled down, then you can say that yt is equal to a imaginary e raised j omega t into g of j omega. But otherwise, if still in the transient phase, you cannot use this simplified formula. You have to use this exact formula. Okay. Now, for t greater than TSS, now we are able to write this formula, and finally, a imaginary e raised j omega t theta minus t omega, and finally, we are removing this imaginary part because we can directly take the imaginary part of this is nothing but sine of omega t minus theta omega. M omega is a real number that is taken outside. And yt is given by a into m omega into sine omega t minus theta omega. Now, what is the meaning of this? Now, so far we have been doing the mathematical expression. Let us see what is actually happening. Here is the time, and we are exciting the input a sine omega t, and the output is given something like this. And we are considering only time beyond TSS. And this axis is not time axis, it is the phase axis, omega t axis. Be careful because omega is always fixed for this particular case. So omega t is a scaled axis of the actual time. And beyond the phase omega TSS or beyond the time TSS, all the transients are settled. And this is the input only. Input has having no transient. This is the input and the corresponding output I am showing. And actually output is here also, but just to show the phase change only I have shown here. And I assume that there is a phase lag of theta omega. Phase lag can be represented like this, a shift in the rightward side. There is the same, this is the rising portion, and the same rising portion will occur only after theta omega. This is the phase lag. In order to represent phase lag here only, I took minus theta omega here. If it was simply directly, if I'm taking as this plus of g j omega, actual argument that represent phase lead, then I have to show this diagram like this, leading the input sinusoidal phase. But that is normally physical systems will have, in general, it will have lag tendency. That's what I have taken theta as the negative of the argument of gj omega. And this represent the, if you observe the output and input together in an cathode ray oscilloscope, you will see two plots like this. One is the input, this is the output, and there is a phase shift. And this phase shift is nothing but the phase of what is actually theta omega. It is the phase of g of j omega. And what is this ratio? This output amplitude is a omega, where a is the command amplitude. So ratio of the output amplitude to the input is nothing but m of omega. So by taking the ratio, you will get the magnitude of the gj omega, and by taking the argument, measured argument, the lag gives the argument of g of j omega. This is how we can experimentally correlate the meaning of the sinusoidal frequency response with the transfer function. And g of j omega has got a special name. It is called sinusoidal transfer function of the system, where g of s is the general transfer function in Laplace variable. If you replace s by j omega, it is called sinusoidal transfer function. And g of j omega can be directly correlated with the experimental result. And the benefit is, this is applicable even for nonlinear system. Only thing is that if you give a sinusoidal command to nonlinear system, it will have the fundamental component at its harmonics. So you worry only with respect to the fundamental component. Take the amplitude ratio of the fundamental component with the command. Take it as g of j omega magnitude, and find the phase shift of the fundamental component with respect to the command sinusoid, and take it as the argument of g of j omega. Okay, this is the concept. Now, only thing is how we will find it out in mathematical way, programmatical way. That is what I explaining using the Fourier series concept. You have all studied the Fourier series. That is, if you have a sin omega t and asymptotically stable nonlinear system, that's what now we are considering. It is stable. And the output can be expanded like this. Yt is equal to a naught, a DC term, and the fundamental harmonic term, which will have both sine and cosine. And then the second harmonic term will combine. And t is equal to 2 pi by omega, the period of sinusoidal command. And the formula for A1, B1 is given as per the normal Fourier series expansion rule. If you know Yt correlating with the fundamental cosine component, you will get A. Fundamental sinusoidal component, you will get B term. Thus, for a sinusoidal command of A sin omega t, the amplitude of first harmonic is square root of A1 square plus B1 square. And hence, M omega is equal to nothing but magnitude of GGO is equal to square root of A1 square B1 square divided by A. And you can find out 20 log to the base 10 M omega to get in dB. You can evaluate. And the phase is given by the, you have to only find out the in-phase and quadrature component. In-phase component of the output is, because A sin omega t is the input command. So its component in phase with sin omega t is the B1 sin omega t component. And quadrature component will be A1 cos omega t component. And hence the phase shift is given by tan inverse of quadrature by in phase. That is tan inverse of A1 by B1. And tan inverse, there are different tan inverses there. You have to, the quadrant sensitivity tan inverse you have to take. That is, we are very bothered with this. Actual phase lag can be theta omega. Now I put it as phase lag. So the direction of phase lag will be like this. It can be any of this quadrant. So it's because, but tan, you know that there is a rule for tan, something here, the first quadrant, everything will be positive, all silver T. Here, tangent is positive here. So tangent is positive here and positive here, whereas it will be negative in these two components. So by simply taking the ratio, you cannot detect out of this, if it is positive, whether it belongs to the first or third, you cannot detect. And if it is negative, you cannot say whether it belongs to the fourth or second quadrant. In order to find out, you have to clearly see both the part, in phase and out of phase, separately. And MATLAB is a command called ATAN2, tan inverse 2, that will clearly quadrant sensitive inverse tan it will bring. That only we will use in this particular program. So that is the end of this lecture. You can go through it, and Mr. Abhilash will share the program, and you understand the program, apply it to your system, and find the frequency response. And this frequency response will be very useful for you in the future. Wherever you go, you will be applying the same thing. And this particular frequency response is being used in ISRO for finding the nonlinear frequency response of all actuation system. So what you're studying is same as what is being used in ISRO. And I only developed this program long back, some 30 years back, I wrote this program, and same thing only you are learning it.
So can you go to the previous slide?
This one?
Yes, sir. So this is from definition, right? The frequency response M of omega is from the definition, the ratio of amplitude of the. Can you repeat the definition once again?
That is coming from this portion only. No? So the definition of frequency response. First, I explained with respect to the practical system. If there is a system and if we excite with a sinusoidal command, what will happen? And if it is a stable system, I told that all the transients will settle. And if you give a sinusoidal command, initially the output will have transient part as well as the forced part. But after some time, all the transients will settle and the output will be only due to the forcing component. And once we reach that time only, you will be able to compare the forced component with respect to the forcing command. That is the essence of what I have been telling. And under that steady state, we take the ratio, and we found that that ratio is nothing but the magnitude of Gj omega, and the phase change is equal to the argument of G of j omega. This is the meaning of M omega and theta omega. Okay?
Yes, sir.
Sir, can you tell again how we obtained that phase component tan inverse of A1 by B1?
That is a normal trigonometric formula only. If you have a, say, one theta, what is the tan of theta? Quadrature component, the opposite side by adjacent side. Okay. Now you are going to the signal domain only. If you have a, if you can simply expand and see what is the meaning of that. Here we have sine omega t. What we are actually doing is, say, finally you are explaining with respect to this sine omega t minus theta omega. Okay, you expand this sine. A plus B sine A minus B formula, you know, sine omega t into cos theta omega minus cos omega t into sine theta omega. That formula, you know?
Yes, sir.
Okay. In that formula, you find out there will be a term corresponding to cos theta omega and sine theta omega. You try to find out what is theta omega from that. So that expansion you will get by simply expanding this, because here writing is not that easy. So you will have two terms here, sine omega t, cos theta omega minus cos omega t, sine theta omega. So the second factor in both the terms, you take the ratio, you will get theta omega. You'll get tan theta omega, and then tan inverse of that. That is how we get. That's the meaning of this concept of this one. This concept, both are same. You find this and apply it to that formula and equate, you will understand.
Understood, sir. Thank you.
Okay. All right.
Yes, sir.
Okay. Okay, I'm stopping.
Thank you, sir.
Thank you, sir.
Thank you,
you,
sir.
sir.
Thank you, sir.
Thank you, sir.